All right, guys. Can you guys hear me?
Yes.
Okay. Thank you. Okay. Let's get started and just for the quiz tomorrow. I just posted another announcement to make it a little bit more clear. But basically, what you're gonna do is you're gonna see the quizzes open up at your session is 2. So 2 o'clock it's going to be open, so you can just start it. The whole time frame for the quizzes, this quiz is actually from the 2 p.m. to 2:45. So you can just start a little bit late, like a 5 minutes, 10 minutes, but still you're gonna get a whole the 30 minutes, which is 35 now minutes of the quiz. So you don't have to worry about the kind of you got be late a little bit by just setting up the lockdown browser or something like that. You're still gonna have 35 minutes, so don't worry about that. Then what you're gonna do is you're gonna see a bunch of questions coming up in order with multi-choice problems and 2 problems at the end of the to solve actually write down some equations and draw some lines, things like that. Then what you're gonna do is submit the answers for the multi-choice problem. Then you don't have to put the answers for the written problem. All right. Then you're gonna just working on the paper. Then if you just finish it, you can start taking out your cell phone to take the pictures of it to make the PDF file, something like using the Microsoft lenses. All right. Then you can do it in front of your lockdown browser. I'm okay with that as long as you finish solving the problem. Just do not attempt to solve again because once you just open up cell phone and taking pictures or something behave weird, then it's gonna just raise a flag in the lockdown browser. So I'll take a look at it. But at the end of the exam, I'm not gonna just care about that because it's time for the scanning and preparing the file. Then when you just get out of the quiz and exit the lockdown browser, then you can just go to Canvas and just post the PDF file to the file upload box I prepare on the homepage. Then the thing is, I just limit the time after exiting the lockdown browser by 5 minutes because, just to minimize the time you, just surfing around or just working on the other stuff before you submitting the file. Okay, it's gonna take like 1 or 2 minutes once you have a PDF file. So please do it right away when you just finish the quiz, and that's the kind of key points of this exam. And otherwise, you can do whatever you want in front of the lockdown browser. Just do not attempt any kind of academic misconduct at all. All right. Any questions about the quiz? Any formatting, coverages, questions? All good? Okay. So I'll just see if you have any other problems with the online quiz this time. Then you can just make adjustment for the exam. But I haven't had that much of a problem using the lockdown browser and webcam monitor before. So hopefully it's going to be okay for this course too. Yeah. Let's go to chapter 7 now. Now we kind of shift our gears to some little bit different analysis, which called the dimensional analysis, similitude, and modeling. So what we are doing in the fluid mechanics here, especially the second course, is the lab, right? So we are taking the data and data and data. So you're gonna end up having a bunch of data and full of data sheets after the experiments. Even if it can be a simple, relatively easy experiment, so you're gonna have a bunch of data set. So problem is how you're gonna deal with that. Can you present the data like in the certain way to present the others can just look at it through the plots or the tabulated data set to find something reasonable and meaningful value out of it. So you don't want to run the experiments every single problem. For example, let's just think about the duct flow that we did. We have a duct flow out there and trying to find the velocity and a velocity profile. And also we're going to end up, figure out it's a laminar turbulent or like a pressure drops along the actual direction of the pipe. And the problem is if you just change a little bit in the diameter, or if you want to change the air speed, of course, air speed is easy to change. If you want to change the medium of the fluid, like from air to helium, air to argon gas, things like that, then are you going to just run the experiments over and over? Are you going to set up the huge giant device with a different diameter every single time? No, that's not what we are doing as an engineer. So when you think about the wind tunnel setup for experiments, actually they have just one wind tunnel. We can just change a little bit of the airspeed or things like that, but still we are not going to build another wind tunnel to run another experiments, right? That's the key. So how are you going to justify the result from the same data setup from the same lab, then apply to the different dimensional, different similar experiments or the similar system? So that's really the dimensional analysis, and the materials we're going to cover in this chapter will be really useful when you think about those situations. So that's what you need. Just let's just come up with one of the example, and you can just keep talking about the dimensional analysis. So we have done the duct flow. So that's the one of the example problem today. So think about the laminar flow, incompressible with the Newtonian fluid through a long, smooth wall, which is no roughness at this point, the horizontal circular pipe. So which is phosphorus flow. Then we are looking for getting the pressure drop per unit length, which is we can just measure like inlet pressures and inlet and outlet. All right, it's not that easy. You have to think about the velocity profile, velocity, the pressure drop along the pipe. Then it's because of the viscosity from the surface. Well, it's not that easy to measure it. So you're gonna just run the experiments over and over. So we have variables that says in order to find the pressure differences, the diameter of the pipe is going to be the kind of important variable, right? If you just make it small, it's going to have a faster flow. If it has the same volume rate of flow, so it's going to change a lot. And the density of the flow, viscosity of the fluid. So those are two the characteristics of the fluid. Then the most important part is also the air speed, which is flow speed. So those are the variables that we can think about for these experiments. All right, so now you want to run the experiments. What are you going to do? Usually we just make all the variables at a constant or at a fixed level. Then you can change one incremental change for the one single variable, right? For example, like for pressure drop, when you change the velocity, we have to fix the diameter of the pipe and the medium of the fluid, which is, let's call it air. Then just keep it as a constant to find the trends of the pressure drop. Okay, so this delta PL is basically delta P over L. It's a unit, the pressure unit per unit length. Then another thing is we want to change the diameter and measure the pressure drop. But we have to fix the velocity and the density and the viscosity, of course, to find the trend. All right, when you want to change the medium, it's the air or argon gas, a different gas, then density changes, but it's really hard to control the viscosity because it is also the characteristics of the fluid. It's really hard to do it because we also have to change the temperature, pressure, the atmospheric pressure to control it. But let's say we already did it. So we have the data. And also the viscosity. Fix the density and just change the viscosity over time. Yeah, it is pretty much impossible, but let's say we did it, okay? Then we have all the data sets, something like this. Then you want to just show it to someone else. I ran a bunch of experiments and I'm just presenting my data. But then someone says, all right, we kind of have a little bit of a problem. I want to see that diameter variables. We want to change a little bit of the density here. It's not 1,000 kilogram per meter cube. I just want to set it at 1,200 kilogram per meter cube. Then you have to actually run this whole experiment again, right? It's not the case for us. So these types of experiments only apply to the specific variables at as a constant. So if you want to change one variable out of 4, then the whole thing has to be rerun. So after this chapter, now you can just narrow down the 4, actually 5 here. We have a pressure drop is also the variable. So 1, 2, 3, 4, 5 variables. We can narrow down to 2 big group of the variables. Then just you can run the one experiment and set up the one trends of the variables to show this whole experimental data. So you don't have to run any more experiments. Just you can run 1 or 2 to find this relationship between the 2 big group of variables. We call it as a dimensionless group called pi terms. And one of the very common example is a Reynolds number, or D, so both are same. So we use the Reynolds number a lot. It's just a number when we change the velocity? No, it is rho VD over mu. So it means when you change the density, okay, it also changed the Reynolds number. Velocity, that changed the Reynolds number. The diameter of the pipe, it changed the Reynolds number. So any changes can be just implemented into the Reynolds number. Then whenever we have a graph like that, whenever you change the like a V, we change the V. That is change the just full Reynolds number. Then you just find the trends. Then you can find the pressure drop here. Of course, the changes of the velocity also apply to this pi term, but still you can just find the relationship between the 2 pi groups, which is pi terms. So when you just have all the variables known and change one thing here, then you just find the point and get the value of this dimensionless group. Then you can just calculate the delta PL out of the dimensionless value, okay? So that's just conceptual approach at this point. Now you're gonna know how you apply this theory into the application. All right. So we call this theory as a Buckingham pi theorem, and we're gonna just come up with a bunch of pi terms, or pi group, which is dimensionless group, non-dimensional variable, like a Reynolds number. Okay. So it says when the equation has a k variables, which is number of the variables, is a dimensionally homogeneous, which means all the net dimensions are 0, or net dimensions are same on the both sides. If I have like a velocity, let's say just a meter per second is a velocity on the left side. Then on the right side, let's say we have AT with the acceleration with the time s. So both sides, we have a same unit. That means it is a dimensionally homogeneous, okay? So whenever we have an equation that involves a bunch of variables is dimensionally homogeneous, then it can be reduced the relationship among the k minus r. So k is we have a number of variables, and r is a reference basic dimension, which we have normally 3 in the fluid mechanics, and where the r is the minimum number of the reference dimension required to describe the variables. So that means if we have a, let's go back here. I'm going to go up a little bit quickly here. So here we have a, how many variables do you have? P is also the variable, right? Pressure, diameter, density, viscosity, velocity, 5. And basic reference dimension, basic dimensions are, we have a, this is mass, length, and time. Or you can also use the force, length, time. So either one is okay, but let's just focus on the one atom. If we have a mass, length, time to describe all the variables, yeah, of course we can do it, right? Everything is consists of the mass, length, time. Then we can have a 5 minus 3, so we have a 2. Okay, then there are 2 dimensionless pi terms in this case. Can you go back here? How many? You have a 1 here, another one here. This is pi 1, this is pi 2. We have a 2 dimensionless variables here. Of course, we have a little bit of a relationship in between, so we're going to just talk about it later. Anyway, that's how you calculate the number of the dimensionless group here. Okay, so any question? So reference dimensions also includes the temperature too. We call it data. But in fluid mechanics, it's not applied to fluid mechanics. There's no way we can just use it, all right? So, but if you go to thermodynamics or like apply the fluid mechanics, when you just deal with the flow with the temperature and the different pressure, then you will have 4 reference dimensions, okay? But now we just have 3. So you don't have to worry about the temperature at this point. This is table 1.1. If you go back to the chapter 1, you can see this unit systems. Then you're going to just look up this a lot from now. Of course, you're going to just memorize pretty much all for the fluid. Oh, let's take a look. So here, FLT is a force length time. This is a mass length time. You can just interchange one to another, of course. Force is what? MA. In the unit based, it is kilogram meter square second square. So it means how you can change it. This one is just F. This is a mass, the length, time to the minus 2. Okay, so you can convert F to the MLT system or the MLT to the force system like that. Of course, the length and the time are common, so you can just go back and forth. So how are you going to do it now? All right, this is now the details of the steps when you find the pi terms. Then it can be a little bit confusing, trying to explain step by step for you to understand all of them. So then once you just finish this step, 1 to 9, then you can just directly apply to the example problem. All right, first, we just bring the Bose flow again. We have a pipe, circular pipe, and flow in there. We have a viscosity, we have a density, and we want to know what the pressure drop per unit length. This is P subscript L. Okay. So we have all the variables here: diameter, density, viscosity, and velocity. First, list all the variables that are involved in the experiment here. All right, if you have anything else, you can just add it. Any dimension must appear in at least 2 perimeters. Okay, let's just take a look. So what you're going to do is just express all the units here. Delta P, D, rho, mu, and V. So what's the pressure drop? This is L. So pressure drop, it means Pascal per meter, right? So that means Newton per meter square and 1/m. Okay, so kilogram meter per second square, then meter cube. I just erase one of them. That means kilogram per, where is it? The m square s square there, right? It means we have converted into the MLT, then it's going to be mass, then length minus 2, and then T to the minus 2, right? So that's how we can convert it. ML minus 2, T minus 2. So what else? We have D, which is diameter. What's the unit? Just length. So you can just have 1L. Density. So mass divided by the volume. So kilogram divided by the meters cube. So just M divided by the L minus 3. How about the mu? Okay, let's just go step by step. So let's use this space. Mu, when you have a units of a Pascal second, right? So Pascal is Newton per meter square. Second, again, kilogram meter per second square, meter square, second. All right, I erase 1, erase 1. It's going to be kilogram per meter second. Okay, so it's going to be mass, length minus 1, time minus 1. Okay, here we have mass, length minus 1, time minus 1. And the velocity, meter per second. All right, L, T minus 1. If you go to a table, you can find that all. Like, for example, viscosity, of course, dynamic. We have a M, L minus 1, T minus 1, right? Do we have a pressure drop here? Yes, here is the pressure. We have a L, the M, L minus 1, T minus 2. And we have a unit per unit length. You can just divide by the one length more. Then we have all of them. Okay, that's the up to step 2. The next step is to determine the required number of the pi terms. Okay, how many variables do we have? Of course, the pressure drop per unit length is the one we are looking to find, determine, but still that is a variable. So we have a 1, 2, 3, 4, 5. K is a 5. Then R, the reference dimension. How many do you have? M, L, T. There's no temperature, so we have a 3. So number of pi term is going to be 5 minus 3, 2. You're going to have a 2 pi terms after this analysis, like we have in the previous slide. All right, step 4. Select a number of repeating variables where the number required is equal to the number of the reference dimension. So this, from this part, it's going to be a little confusing. What is a repeating variables? We're going to just use it over and over. That's why we call it repeating variables. And you have to choose 3 of them out of 5. And there's a rule, but it's kind of not obvious. But there's no wrong answer if you choose the wrong, different one from another one. That's fine. So there's no 100% correct, 100% incorrect answer at this point. You can just choose anything, but there's a few tips to make it easier. All right, repeating variables. You have to choose 3 of them because it has to be same number of the reference dimension. We have pressure drop, diameter, density, viscosity, and velocity. So first tip, each repeating variable must be dimensionally independent. That means just they're not supposed to be same. Something like if we have a 2 length, like diameter and the width, let's say we have a diameter and length, let's say we have, then it's going to have the same unit, L and L. You can't choose both of them. You choose one of them. At this point, actually, all the variables have a different set of units, so it's not applied to this case. So you can choose anything here out of 5. Let's go back to another tip. Dependent variables cannot be a repeating variable. What is a dependent variables? It's the one you're trying to determine. So we are looking to find the pressure drop per unit length. So pressure drop is the dependent variables based on the other variables. So that should not be the repeating variable. So this is not. No. And third, do not choose the variable whose effect is questionable or trivial. At this point, everything is important. So I'll just skip this point. Final, select variables as close to dimensionally pure as possible. So this one can be a little bit different. It's not hard rule. You can choose another one. That's fine. You will have a little bit different result. You can just convert it later. At this point, let's go back to here. All right, this is not the one you can choose. We can choose the D because it's simple, right? And independent from others. All right. Velocity, yes. And we also include all the dimension here. So that's why here. Did I include that one here? Okay, so the one thing is you have to include all the variables with each basic dimension. So MLT should be all included. So we have a TL choose D here because of the L. We chose a V because of T. Then we have a 2 choice left, rho and mu. What are you going to choose? You can choose either of them. That's fine. You will get the same answer. Of course, not exactly the same. You can change it. But the easy way is to find the pure and simple one. All right, the one has a ML components. Another one is M, L, and T. So I'll just choose the rho for make my life easier. All right, it's not that obvious, but if you just do this stuff over and over, you'll just get some sense of how you choose the variables first. But again, if you choose a mu here, that's totally okay. It's not incorrect answer. You can just keep moving on to the next step. All right, so from the step 4, yes. It's a number of repeating variables should be the same number of the reference dimension, MLT. We have 3 of them. In fluid mechanics, we only have 3 basic dimensions, so we can choose 3 out of 5. So the pressure is the dependent variable, so I'm not going to choose it. So I choose the D and V, and we have to choose one more between the rho and mu. Then I just choose the rho because I just wanted to make it simple as possible. Pressure is the one we are looking for. So we're trying to change the variables rho mu v to find the effects on the pressure. So if you're interested in the pressure drop, then you're not going to choose as repeating variables. Okay? Yeah, mu and rho, actually you can choose either of them. I'm going to just do it. So I'll just choose one to another and solve separately and see if those are the same answer. But it's not going to be the same, but we can make it same later. So let's say we chose one here, the rho. So this is the 3 repeating variables of my analysis. The next step, the form a pi term by multiplying one of the non-repeating variables by the product of repeating variables. Okay, so here we didn't. Oops. So let's say we have now here. So this 2 is now non-repeating variables, right? Then what it says is form a pi term by multiplying one of the non-repeating variables. So one of them, let's just choose the one here, pressure. First pi is delta PL. And by the product of the repeating variables, d, rho, v, then each raised to the exponent unknown. So a, b, c. Okay, this is my first pi term. A, B, C is unknown. All right, now the key point is we just make this pi term dimensionless. All right, that means this is the same as the delta P L D rho V, but now it should be all zero here at the end. Okay, so we can just tweak the number, the exponents A, B, C to make things balanced. That's what we're going to do. How are you going to do? Just express those pi terms with the units now. The delta P we have ML minus 2 T minus 2. Then D is L. I put the exponent A. Then rho, we have ML minus 3 B. We have a V, so M, not M, L T minus 1. And we have a C here. Okay, that should be delta PL 0, D 0, rho 0, V 0. Oh, let's just change it like that. MLT 0, 0, 0. Okay, let's make it all 0. So first, choose one, anything, like M. We have 1 here. We are just talking now, just dealing with the exponents. So we have a 1, and here 2. So we have a exponents of the B there. So plus B equals 0 on the right side. So we know B is a minus 1 to make things dimensionless. L, we have a minus 2 here. Here another one, A. Here another one, minus 3 multiplied with the B, minus 3B. We have a 1L here with C. So plus a C. Make it 0. I don't know. So let's go to T. We have a minus 2 here. Then we have a minus 1 with the C. So minus C equals 0. Then we know C is a minus 2. Then when you plug that in, you have A equals 1. All right? Then you can just plug that into the pi term here. So you can have pi 1, which is the dimensionless group is still have a pressure without any dimension here. This is 1. Then what is A? 1. So D is there. Rho, B is a -1. So I'm going to put that into the bottom here. The V has a -2. So it's going to be V squared. We found one of the dimensionless variable here. All right. What did we say? We have a 2 dimensionless variables, 2 pi terms. So we found one, we have another one. What is another one? Second pi term is one of the non-repeating variables, mu. We finished with the delta p, so now it's time for the mu. Same process. There's a mu. We have repeating variables, d, rho, v, but d, rho, v with the exponent a, b, c. Then we want to make things all 0. It's actually a little bit misleading expression, so. Dimensionless. Okay, that's a little bit misleading, so I don't want to make you confused with this expression. So just make this all dimensionless. Now just express all variables with the units. What you have is a mu. If you go back to up there, so mu we have m, l minus 1, t minus 1. So just put that in, m, l minus 1, t minus 1. And we have a same dimension L, ml minus 3, and lt to the minus 1. Then we have exponents for each here, there, here. Then we want to make it all non-dimensional. That's the right expression. So one by one, for the m, mass, we have a 1 here, and we have another one here, plus b, and there's nothing, should be 0. B is -1. So we can go for t first, because it's going to give you the number. We have a -1 here, then here -1 with c, so minus c equals 0. So we can have a c is a -1. Now time for the L. We have a -1 there. We have a here. We have a -3b. Then here another one's c there. And this should be 0 too. When you plug that in, it's 3 minus 1 minus 1 is just 1. So a is a -1. Okay, so pi 2 is we have a mu there, and all the exponents are -1. So rho v d. We found another one here. Okay. So next step, the 8th is just make sure you have the 7th step is make sure you have a dimensionless group. If you just plug all the units into P, D, rho, V here, then you're going to have dimensionless. Check dimensionless. You can check this one, okay? And the 8th is when you know the customer uses something like a Reynolds number. Can you find Reynolds number here? Yes, this one look very similar to the Reynolds number, right? It's just reciprocal. All right, we are dealing with a dimensionless group, which has no dimension at all, unitless. Can you multiply with the constant, any constant? Yes, we can. Can you make it square, power to the 3, power to the 0? Can you take the reciprocal of the dimensionless group? Yeah, everything should be dimensionless. So actually, when you have the dimensionless group, pi term here, you can manipulate whatever you want. In a way, I'm going to just take the reciprocal of the pi 2, then it's going to be rho v d over mu. Still dimensionless group. So you can just use it. This is a Reynolds number. Great. So if now we have a two-dimensionless group, then for the experiments, now you can design the experiments in a really simple way. You just need to plot the data with the two variables, which are group of the variables now, pi 1 and pi 2. Because the Reynolds number is the one we know as a kind of customary dimensionless number. So you can just design. So let me just write down the expression. So pi 1 have a little bit of the function of the pi 2. I don't know what the function is. This is an unknown function. It's not given after this analysis, but you can just find this function from the experiment. When you set up the experiments, then run it to find the pi 1, which is rho vd mu, pi 2, which is delta p d over rho v squared. Then let's say we have the data here. Okay. This data show you what the function here, phi. Okay? That's the kind of relationship between the two non-dimensional group. Then this graph, when you have this graph, then you don't have to run another experiment at all. Okay, I want to increase the diameter of the pipe. What are you going to do? Increase it. D prime. Then this whole number, Reynolds number, going to be changed. Go another one. And look up the data here. Then plug the number, plug the number, plug the number. Then you find the delta P. Okay, I want to change the density of the fluid here. Then I just put the different rho here. It's going to change the pi 1, which is a group of the variables, Reynolds number. Then let's say it was located in this position. Then you can just look up this, another pi term, then plug the numbers and find the delta P. You don't have to run the experiments over and over when you change the variables anymore. That's the one of the biggest advantage of the dimensional analysis. Then, of course, it's a little bit confusing at some point. I don't think I have a time for the further process here, but I'm going to pick this up next week when we choose the repeating variable here for the mu instead of rho, then see if we have a same result. Okay, that's going to be the most confusing part of the dimensional analysis, but you can actually do it. All right, so I'm going to post the homework tomorrow after the exam. It's going to include a little bit of problem in this chapter 7, but please just skip it and working on the example 7.1 here. All right. Then you might have some little bit of confusion when you just solve this problem. But please just take a look, and at next week, I'll just show you how I solve this one, and also when you choose the different repeating variables, how it's going to change the pi terms and how we manipulate the pi terms to make it the same one we have from the previous step. Okay, I'll just stop here for today. For the quiz, if you have any question, please let me know. And just announcement for the office hour, I usually just sit on the desk and just wait for your call, sitting on my desk. So please just shoot me a message or email if you have any questions during the office hour. I'm pretty much ready to talk to you guys. You can just call me if you can. That's fine too. I'm fully ready to give you any answer during the office hour. All right? Just trying to advertise my office hour. That's why. Okay, guys. Have a good rest of the day, and I'll see you tomorrow. Of course, not see you tomorrow, but the exam. So, all right. Bye. Yes, sir.
So you said repeating and looping, is that?
Mm-hmm. So it depends on the situation. So the repeating variables, you can choose any repeating variables at this point. Like think about the D. That's pretty much impossible, but let's say we have a pressure drop. We know the value. You just want to find the dependency of the, let's say what? Velocity based on the pressure. All right, this is a better application. Let's say we have a pulsatile pumps there, then we know the pressure input into the flow, the pressure driven flow. We want to know the velocity now, mean velocity. Then velocity is now the dependent parameter. So it cannot be a repeating variables if the problem set up like that. So in that case, let's go back to here. Then this is the different setup. We have a pulsatile, we just have a pump. We have looking at the manufacturer spec sheet, we know the pressure input to the flow. Okay, then we have a setup in the tabletop with a certain diameter, and the flow is, let's say, water, rho, and mu. Then we're going to run the experiment, looking just to see how much velocity we can find from the flow. All right. Then the V is the one we are looking for. So when you choose the repeating variables, you want to ignore the V when you choose the repeating variable. So that should be the non-repeating variables in the Python. So in that case, you can either choose a P, D, rho, mu. Then I'll choose D, rho, and either mu or P. Okay, because P and mu both have a MLT. So I may choose one of them with the simple one, the mu first. So D, rho, mu is going to the repeating variables of my analysis. But of course, you can choose the P too. It's going to give you the same answer, by the way. But that's how you can approach to the data sets or the system of the experiments. So I think it's better to solve the problem over and over. I don't think I have time to go over more stuff today. But next week I'm gonna just show you how I solve the problem. Then you can just trying to solve the homework problems and the example problems. That's gonna make sense a lot. Yeah.
Professor Lim, I have a quick question.
Yes.
So regarding the lab with trying to find the mass flow rate. So I know we derived in class the volumetric flow rate for a steady state laminar flow and a cylindrical. But so I see that it's dependent upon the pressure change is related to the z-axis, but isn't there not a pressure change?
No.
So it's zero then? Like that's where I'm confused.
It's non-zero. So from the data set, what do you have at this point? you have a velocity profile, right?
Mm-hmm.
Okay, can you find the volume rate of flow out of the velocity?
Well, velocity multiplied by the area.
Yep.
Yeah.
Exactly. So instead of multiplying, you're gonna just take the integral over to the area, right? From the radius r 0 to r. So you can find the volume rate of flow. Then from the volume rate of flow to the mass flow rate, can you convert it without any equation?
Well, you multiply by density.
Yep, it is. So when you have a density, you can just convert that into a mass flow rate. Then the density is the one you calculated based on the absolute pressure and the temperature in the lab.
Yeah. Okay.
Mm-hmm.
So when you multiply by that density, it changes the pressure dependent upon z. Okay. And it changes it to
Pressure dependence, gee, what does that mean? So I'm looking at the formula at this point because it's not because the formula is not applied to our situation, but also we are just trying to find the mass flow rate regardless the pressure drop along the pipe. Because we measure the velocity, so we don't have to know the pressure drop to calculate the mass flow rate. So you don't have to go into the pressure drop at this point. Yeah.
Okay.
It's all about the flows, velocity, volume flow rate, and the mass flow rate. That's all I asked.
Mm-hmm. Okay. And then I was calculating my Reynolds number. I was getting a really low Reynolds number. I got like 10 and 15.
You gotta go back to calculate it again. Yeah. Either it probably wrong units, wrong conversion, something like that. So
Okay.
it actually needs to be more than like at least 200,000 or 20,000 or something. That's going to be much, much higher than that.
Okay. All right. Yeah, I'll go through and try it again. When I did it with metric units, I got like 30,000. But then when I went to standard units, I got like 10. So something's up.
Okay. Yeah, just to make sure you have a right units for all the variables and make sure you have a right conversion from one to another. Inch to feet, feet to meter, you know.
Yeah.
Okay.
Okay. Thank you.
All right. Yes, sir.
We have 45 minutes, does that mean?